Well, a dream, when you are doing software development and interested in interaction, a dream will be to be able to use docking as a tool to predict interactomes. So assume that you know all the proteins in an organism. You could do cross-docking, so all against all. You have your perfect scoring function, which selects the best model every time. So your docking software is perfect in an ideal world. And now if you want to predict the interactome, you need to be able to assign a binding affinity to all those models that you have generated. Because when you do docking, I think there is no docking software that's going to tell you this is not binding. You always get a model, okay? Or the software crash and then you don't get a model, but otherwise you're always going to get a model. But what defines at the end if the complex will take place in real life or not is the binding affinity. And of course, the concentration of the proteins in a cell, which is another variable, which is not very simple to get access to. Now, the binding affinity is defined as the concentration of, say, the ligand that you add to your solution at which 50% of the binding site of your receptor is occupied. That's the definition. So the question is, can we actually predict binding affinity by docking or, well, by molecular dynamics simulation, maybe? I'm not going to speak about molecular dynamics, but so this is the work of Panos Gastritis, a former PhD student in my group. And we were not going basically to decide. So doing the docking of the entire proteome, cross-docking will not make sense at this time. There are too many limitations, conformational changes, so scoring is not perfect. So let's start simple. And we're going to take crystal structure of complexes for which we know the binding affinity and try to assess if the scoring function that we are using are able or not to predict correctly the binding affinity. So we have no structure problem. We have the perfect structure, assuming that the crystal structure is the perfect structure, and we just try to test our scoring function. So to do that, first, of course, you need to have a benchmark, a structure-based benchmark, and we want to have both the free form of the proteins and the bond form of the complex to be able to assess the impact of conformational changes on our ability to predict binding affinity, and you need to know the binding affinity. So this is not a simple task to assemble such a benchmark because often binding affinity data are buried in the papers. So there are no really good database that provide you all the data. The methods are buried, so it's a bit messy. So we teamed up with several teams in the field, several groups. So Paul Bates in the UK, ZP Wang, her group is developing the ZDoc software, Ian Marl, and Joël Janin was basically Joël is the father of docking. Joël and Shoshana invented docking as I explained to you at the beginning of my first lecture. So we had a set of about 140 complexes in total, which represent different types of interactions. This is a non-redundant set. That's also important. And we have a distribution of complexes over different type of binding affinities. So you might have very high binding affinities, say sub-nanomolar binding affinities. Then you have the, say, micromolar to nanomolar binding affinity, medium, and you have low binding affinities where the KD is smaller or actually larger than micromolar. So this is the data set that we have at hand, and we have crystal structure for all of those, both in the free state and in the complex. So what did we do? We took this data set, we took the crystal structure of the complex so that the conformational changes do not play a role, and then we assessed at the time, so this is 2010, 10 years ago, a number of scoring functions that were popular at the time. Fast contact, fire dog, dfire is also still very popular these days. We use our Haddock score, Rosetta, also very popular and still going very strong. Z-rank, that's from the ZDoc. PISA, that's from the PDB. PISA is used when you deposit complexes also to get characteristics of the binding site. At the time, it was giving you free energy, enthalpy, entropy, everything. And the other one are over docking scores. So this is what we have. So we do this, we calculate all the scores for the crystal structure, and then we look, is there any correlation with the binding affinity? And this is what you get out of it, and R square about 0. Okay, so that's bad news. And just to give you an idea of how this looks like, so here you have 9 plots which correspond to 9 different scores. You have on the y-axis will be the score predicted by the software or the scoring function. On the x-axis are the experimental binding affinities. Haddock is in there, Haddock is here. So we get a correlation of R of minus 0.16. The best one in this set, minus 18. So there is, I think, the Z rank. Well, minus 32. I think FireDog was doing okay, but minus 32 has basically no predictive value. Okay, you could try to draw a line in this, but it doesn't make any sense. So you cannot really make predictions there. So this is just to give you an idea what should you expect for different type of correlations. Okay, and if you are in this gray range, basically there is no predictive power. Now we took a subset of complexes because also finding reliable data is tricky. So this is a subset of 46 complexes for which we trust much more the binding affinity data that we have. And you see the best calculate here was, I think it was Attract in this case, is giving you an R correlation of 0.5, minus 0.51, okay? Now, the first model of binding affinity predictor published was in '92 by Horton and Lewis. And their model was a very simple model. It was only using the amount of surface buried at the interface between your complexes. And it was doing that by splitting the amount of surface between polar and non-polar surface. So if you go back to this paper, 92, they tested that on 10 complexes and they were getting correlations about 0.9. So it looked in 92 that the problem was solved. The amount of surface between the proteins tells you the affinity. Now, if you assess the same, you use the same model of Horton and Lewis, but then on this benchmark of 140 complexes, you get a correlation of about 0.5. For the complexes that do not have any conformational changes, it's 70 points. So these are the dark points here. And for the flexible binders, and flexible binder means there's a conformational changes of at least 1 angstrom. So 1 angstrom you would think is nothing, but if you do that, you see that the error is completely insignificant. So small conformational changes in terms of binding affinity are already giving you problems. So this correlation coefficient for this buried surface area model is as good as the most fancy energetic scoring function that you can think, which is probably the Rosetta one, okay? So that's not very encouraging news. So there are many reasons why things are not working maybe very well. First of all, you know, they are limited. Well, if you are more someone in a software and simulation side, you will blame the experimental people first, and vice versa often. But okay, there are limitations in the quality of experimental data. You will find in the literature data for the same complex that give you different values. So you might not always know exactly, you know, what was the salt concentration, temperature, pH at which the measurements were done, and these will all introduce errors in your data. We are using crystal structure. There might be ambiguities in there. We might be missing cofactors in our calculations. We might be missing the effect of water. Conformational changes are going to play a role. And I think an important point when you think of scoring based on docking function is that we always, neglect the free state. So if you have this very simple free energy landscape here, so this is the free energy of binding, and you have a landscape. Here you have the bound state, and here you have the free state. So we have two types of complexes in this example. So we have a circle binding to a triangle, and we have a triangle binding to a square. So if you were to assess their binding affinity or predict only based on this state, you would predict that they have exactly the same binding affinity. And this is what we are doing when we're doing scoring. In most cases, we score based on the model of the complex that you have. But in this example, the difference in binding affinities, okay, which is the difference between the bound state and the free state, comes from the free state. Because here we have a higher energy, free energy of the free state than this one. This is a lower free energy, and it means that this one, the AC complex in this example, binds stronger than the AB complex. Now, if we don't consider the free state in our binding affinity prediction, then that's one of the limitations of things. And then conformational changes, entropy, all of that. Most of the scoring functions that we are using in these fields, they are at best approximating the enthalpy and not considering very much entropy, or entropy is maybe hidden implicitly in some terms. So there are clear limitations. So we had all those data. It was not a large amount of data, but then you do kind of data mining and you're going to look at all kind of correlations. So we calculate many properties of the complexes and try to find, is there anything that correlates with binding affinity next to binding surface area? And here came something very surprising out of this study, is that properties of the non-interacting surface, so the part of the structures that is not at the interface, do show correlation with binding affinity. And the two properties that came up, one is the percentage of polar amino acid on the non-interacting surface, and the other one is the percentage of charged amino acid on the non-interacting surface. So what you see here is that so there's basically a positive correlation. If you increase the polarity of the surface, you see an increase in binding affinity, and there is an anti-correlation with the charge of the surface. If you decrease the percentage of charged amino acid on the surface, you decrease the binding affinity. So this is, of course, surprising because things that are not directly involved in interaction kind of show correlations. Of course, you have to be careful with correlations, okay? It's not because something correlates that there is a causality. And there are plenty of examples that you can find on that. And the one that I like to use always, because I'm Swiss of origin, is that there is a very strong correlation between the consumption of chocolate per habitant per country and the probability to get a Nobel Prize. Okay, if you plot the consumption of chocolate per habitant per country versus the number of Nobel Prize in a country, you get a correlation of 0.9 or something. Okay, does it mean that if you eat more chocolate, you have more chance of getting the Nobel Prize? Probably not, but it's a good excuse to eat chocolate anyway. And speaking of Nobel Prize, I don't know if you follow things next to attending the workshops very closely, but the Nobel Prize in chemistry has been given today to CRISPR-Cas, which is very nice. Jennifer Doudna I should know the name, but okay, it doesn't come right now, but two women got the Nobel Prize in chemistry, fantastic. Okay, so now if you think of electrostatic, you would say, oh, electrostatic, that must be affecting the on rate of the complex. So you change the polarity of the charge of your protein, and this is affecting the way at which the protein bind to each other. Okay, you change the attractive power, basically, of the protein. Now, if this was true, there should be a correlation with the on rate and not the off rate. And for a number of complexes, we also had the on and off rate. And you see here that the correlation is actually with the off rate. So dissociation of the complex and not the association of the complex. So this attraction argument doesn't hold. So we have to find another argument to explain, actually, to try to find if there is a causality to that. So now we reason that if there is indeed correlations between the polarity and charge of the surface, if this is a true effect, this might be conserved across different species. So in evolution, you might see this effect. So this is something that you can test. So we took 44 different complexes, the one for which we trust the result. And if you plot for these complexes, basically, so they are ranked based on the binding affinity here on the x-axis, and you plot the percentage of charge and polar residue, you see that there is a lot of variation. So these are the 44 non-redundant complexes. Now, if you take one complex and you start generating homology models across evolution, so you go back in evolution, this is shown here for two of those, so one XQS and one GLA, you see now that the properties they are still fluctuating, but they are not fluctuating that much. So it seems that the general properties of the surface are conserved through evolution. And you see here on the x-axis, now you see the sequence identity between the protein sequence. So you can do this analysis at the structural level by looking at homology models, or you can do the analysis purely from sequence alignment, so you don't generate 3D structure. And if you compare what is the standard deviation, basically, of this variation that you observe here between the non-homologous complexes, this will be this part, and for one complex, but then going back in evolution, you see that the sequence variations are much smaller in those cases if you consider evolution. So there seems to be an evolutionary signal about these surface properties. So now can we explain why polarity and why electrostatic in this case? So polarity, when you think of polarity, at least when we thought of polarity at the time, we thought of water. There are proteins that are known to be antifreeze proteins that have been studied. So some organisms have antifreeze protein to protect them. They live in very cold waters. And one of the properties of those antifreeze protein, among others, is that they have rather high polarity of their surface. So polarity could have to do with the water. And if you can stabilize the water shell around the complex, you might protect it from dissociation. Dissociation has to come from collisions with other molecules in a medium. You need to provide energy to pass this dissociation barrier. So if you stabilize the water layer around the complex, you might stabilize the complex. So what did we do to kind of test this hypothesis is to look at high resolution crystal structure in the PDB, which have a resolution below 1 angstrom, and analyze the water at the surface, and distinguishing between water close to polar residues or charged residues or apolar residues. So first of all, if you look at the B factor, which defines how well defined is the water position in a crystal, so you see that and then you look at how many contacts does the water molecule makes with the protein, you see that water molecules that are very well defined usually have quite a number of hydrogen bonds contact with the protein. So these are all the water. And now you can do the same analysis, but distinguishing between contacts that are made to charge polar or apolar residue on the surface. And you see that the polar residues and apolar actually show more contact than the charged one. Okay, so with decreasing B factor, stable waters tend to contact more frequently polar and apolar amino acid. And this is kind of so it's not a proof that this is the reason why you observe this correlation, but it's an hypothesis. It's not easy to test this hypothesis experimentally, actually. We did studies by molecular dynamics of the system. So we took 5 complexes of different binding affinities, run those complexes in explicit solvent, in duplicate, analyze the water residence time on the surface. And again, so what you see here is we can calculate B factors from the simulation. And we see indeed that in simulation, we see similar effect as what we observe in a high resolution crystal structure. So you see the distribution violin plots of water on the surface, the non-interacting surface, and water close to the interface. The rim is close to the interface of the complexes, and you see that there are different distributions for polar and charged. We did the analysis both for the free form of the protein and the complexes. I don't want to spend too much time here. We also look at how long do the water stay on the surface of the protein. Water is constantly exchanging on the surface of proteins. And we see again an effect that the water tend to stay much longer around polar residues on the surface than charged residues. So here the polar non-interacting surface versus charged non-interacting surface. So you see, so these are the polar residues, and you see here down there the charged residues. So there is an effect when you run molecular dynamic simulation, which tells you that indeed water seems to be stabilized at proximity of polar residues. So a theory that it's the stabilization of the water shell that stabilizes the complex does make a bit of sense based on what we see in the PDB and those simulations. And you can do the same analysis that we did from the high resolution crystal structure, but from the simulation, and we see again the same trends. So this was about the polar residues. So now what about the charged residues? Can we explain these? So it seems strange that charges go away. Sorry, that's what's happening at home. Okay, so charges on the surface would affect the binding affinity, and they destabilize it in our model, at least what we're observing. So we didn't do very fancy molecular dynamic simulation. We follow here a very simple model, which we call the onion model, to calculate the impact of the electrostatic on the interface, actually. So does the interface in the complex feel the electrostatic of the surface? That was the question that we addressed. So we basically did, we place ourselves at the center of the interface in a complex, and then start drawing circles, spheres around the center, and then we calculate the electrostatic contribution of the amino acids, of the charged amino acid to the center, basically, as function of the radius of those spheres that we place. And we do that for the complex, and we do that for the separated protein, and then we take the difference. And this is giving us basically the electrostatic contribution to the binding, kind of. And you see that this effect, so if we don't use cutoff, so we calculate everything, we see that the electrostatic interaction energy goes down up to about 40 angstrom. So it seems here that the interface is sensitive to long-range effect. So things that are happening far away from the interface still seem to affect the interface. So our current working model based on this observation was that we need to consider global surface properties together, of course, with the interface. It's not like there is no thing in the interface. I think the interface is the major component, but if you want to refine your models of binding affinity, you need to consider the non-interacting surface. So this was the model proposed by Horton and Lewis in '92. So it only depends on the interface between the protein, buried surface area, polar, apolar. And our model at the time when we did the work, so this was published in 2014, was yes, the interface is important, but we also need to consider in a model contribution of the non-interface region. And our model has basically this term, this number of atoms at the interface is kind of a buried surface area term, but then it has the percentage of non-interacting charged residues and polar residues on the surface. And this is now the two models. We distinguish cases where there is no conformational changes and cases where there are conformational changes. So this is Horton and Lewis retrained on the new data set. So you get a correlation of 0.5 for the flexible interface, and flexible is very little flexibility still. It's down to 0.16. With the new model, we reach 0.64. It's not fantastic, of course, and then we have 0.32 for the flexible one. Now, is this all theory and nice computing, or is there any reality to that? So we try to figure out if there is support for this model by looking at data of free energy changes upon mutations. So there are databases where you can extract this information, and we classify those free energy changes as function of the distance from the interface. So if you do a mutation in the interface, this can have a huge impact, of course, on the complex formation. It can kill completely your complex, so that's not surprising. And then as you see mutations, so these are experimental data. As you see mutations, when you move away from the interface, you see that up to 5 angstrom, so here you will be kind of still in a rim, maybe. You have changes of up to 4 kcal per mole. But now you're moving really outside of the, far away from the interface, up to 12 angstrom, you might see effects about 2 kcal per mole. So these are not huge effects, but these are small effects. And remember, a lot of interactions in biology take place at the micromolar range. A lot of signaling processes. You don't want to have the signal always on or off, but you want to give it and then it should fall apart. So these are very weak interactions. And those small differences that we observe here at longer distances from the interface might well modulate the binding. So there seems to be something in the experimental data. Now, after this, having done all this work, we revisited actually our binding affinity prediction work. And this was the work of Anna van Goorn in the group. So Anna had been working before a lot on analyzing contacts in proteins and interfaces. And basically, we wanted to see if by just, instead of having say energetics of buried surface area, if we could just use contact as a proxy of binding affinity. So she developed a model which basically considered the residue-residue contact at the interface of a protein complexes by counting all the contacts up to 5 angstrom. And then we're going to classify those contacts in different type of contacts, polar-polar, charge-polar, all of this. We do a feature selection, so this is more machine learning to remove things that are irrelevant. Cross-validation, everything. We use the same data set. So this is the model. If you take all contacts, so we get just purely the contact, so nothing else, we get a correlation of 0.5. So this is at the same level as the buried surface area and the same level as all the scoring function. You also see here that depending actually on the type of data that you are using to generate the binding affinity data, you get different correlations. So these are inhibition assay, fluorescence, which give very poor correlations, and some other get better data. So again, this is showing you that not all data are equal. So if we discard those, we can get much better results. So this one, we're getting to 0.6 correlation by discarding inhibition assay and fluorescence. And then we can train a model. And now you see the final model here, which has, again, different type of contact classified based on the type of contact. But again, the non-interacting surface is part of the model and came out of the automatic selection process. So we get a correlation of 0.73 in this case, and our root mean square prediction error is 1.9. Now, where does that put us compared to a lot of predictors in the field? So you see here a lot of different predictors. Some of them I was mentioning before. So this was Castritis et al. Was the, or say, non-interacting surface work, where you see that we are getting over all complexes about 0.62, 63. If you distinguish, we are doing better for the rigid complexes than the flexible one. And now when we use the contact together with the non-interacting surface, you see that it's, first of all, very stable in terms of prediction capability, both for rigid and flexible contact, giving you a performance of about 0.74. So this was published in 2015, and it's still one of the better and very simple, very fast predictor of binding affinity. So this is now implemented as a web server, so you can run very quickly. It's also available on GitHub, so you can actually download the code and run your prediction locally. It's very fast because it's just counting contacts.